Hello from Cincinnati, everybody. This is Mike Burchak, and welcome to our Smart Controls webinar. I've labeled this as a level 1 session because as I got into it, I realized there's a lot to cover. And there's been a lot of talk about smart controls, artificial intelligence. Different people use different definitions. So a lot of this webinar will be going through and talking about the need to do something better in the industry. We all have capability that we've purchased, we've installed as part of projects. I don't believe that we're using it to its best capability. And we're laying a lot of groundwork in this webinar, and there will be a level 2, possibly a level 3, as we talk more about how we need to be going about and thinking about these important systems in the future. So I am Mike Burchak, Managing Principal of the Industrial Solutions Group, and we do these sessions about once a month and really appreciate everybody's participation and involvement. So it's good to chat and have communication with folks. The Industrial Solutions Group, this is our little elevator pitch. We get involved in a lot of industrial work from an engineering side, various technologies. We do a lot of economic studies and strategic evaluations, and we are also very, very aggressive on the sustainability front. Of course, this particular topic falls in the technology, where we're dealing with automation and how we go about trying to get our systems designed so that they can help us do a better job of maintaining and operating. But as we go through these sessions, you will find that we'll be picking topics that will come from each of these blocks. Today, we want to share information on a few aspects of this. First, we want to share a proven concept that helps to make DDC and PLC-based controls more useful in our industrial utility and process systems. Secondly, we want to provide an understanding of how knowledge-based controls can help ensure systems consistently operate at design conditions, which they oftentimes don't currently. And three, we want to help to increase payout results from improved performance, lower energy use, reduced maintenance, reduced operating costs in general. Again, a lot of people use different words and there are different definitions, so I thought it would be helpful to talk a little bit about that. One comparison I had is sometimes we use the words knowledge and wisdom interchangeably. And I went out and just grabbed some definitions. Well, knowledge are facts, they're ideas. We get them from many things, our experiences, our studies, our research through life. But wisdom's a little bit different. It's the ability to take that knowledge, figure out what we need, and help us move forward with a little bit of insight, a little bit of good decision making that is applicable to life. I heard somebody else define these two as in a little bit different way. So, well, knowledge is knowing that tomatoes are a fruit because they have seeds on the inside. Wisdom is knowing that you don't want to put a tomato on a fruit salad. Well, today we're going to focus on another comparison. We're going to look at data and knowledge. And data is what I see a lot of our control systems currently designed to do. They just provide quantities, operating data that comes in, volumes and volumes of operating data, different quantities, characters, symbols. They come into the computer. In many cases, we're doing a pretty good job of displaying this data out and then giving it to an operator or technician whose responsibility is to keep these systems running. But what the technician, the operator really needs is knowledge, how to use this data to make smart decisions about day-to-day operation of these systems to keep them up and running reliably and cost effectively. And staffing levels continue to be very, very tight. Good resources continue to be very, very scarce in our factories. So if we can get control systems, if we can get some help on turning data into knowledge, that can really help us in a lot of different ways. And I believe we've got the opportunity to do that. If we don't do that well, we start running into a couple of problems. Sometimes we just selectively use data instead of looking at all of it and pulling all of it out, a process referred to as data mining. Another phrase that's been around a long time, we can get into analysis paralysis. We just keep looking at piles and piles of data trying to find truth, but that's really not what it's all about, because there's always more data. There are always other truths that need to come to the surface. I have a little example here. For those of you that know anything about baseball, batting averages are really an important aspect. So if you want to play in the minor leagues, or hopefully the big show, you get up into the big leagues, then you really want to be a good hitter. So here's a batter that's gone through 9 games. We've got hits in the second column, and through 9 games, this player has gotten 13 hits and 41 at bats. And you just look at these numbers and say, well, is that good or bad? And the answer is, well, that's a 317 average. Now, if you've been around the baseball track, if you're hitting 317 in the big leagues, you're going to play every day, and you are going to get some nice contract money out of that. So that's a pretty good batting average. But let's look at a little bit more. Let's say that you were the manager of this player, and you notice that some of these games are really, this guy's just really hitting good, but he's kind of a streaky hitter. Some games good, some others. So one variable that we know that happens a lot in baseball is some batters are better at hitting right-handed pitchers than left-handed pitchers. So we've sliced the data a little bit, trying to understand what's going on. Why are we ending up with so many games where you get no hits and so many games where you get some hits? And that's really kind of interesting, because when you look at this batter's results against left-handed pitchers, he's only 2 for 18 against left-handed pitchers. That's a 111 average. That will not get you in the big leagues. It'll barely keep you in the minor leagues if you can hit a long way. But look at what this guy's doing with against right-handed pitchers, 478. One of the best averages you'd ever get. If you can maintain that, that's great. So now you got a manager, and you got an interesting thing. You got a potential for a superstar here, because on average, really a good, strong ball player, but really doing poorly against left-handed pitchers. And you know you've got people sitting on the bench that can do a better job than that. So the conversation has totally switched from, hey, you're really a good hitter, to you got to get some practice in against these left-handed pitchers, or I'm going to have no choice. I'm only going to play against right-handeds. So good, just a little example of where you go from just data to trying to do knowledge, and this would be a real positive direction for this coach to take this player. You know, how do you improve your game? How do we improve the team because you're improving your game? Same is true in manufacturing. I think some problems you go about, it's easy. You walk around a parking lot and you see potholes in a parking lot. You see problems, corrosion of metal, things of that nature. Some items are really easy to spot. There's a bunch of process HVAC utility equipment. Clearly, this equipment lacks love. It really needs some attention, and you don't have to be a rocket scientist to walk around and start seeing that, hey, there are some opportunities here. The maintenance practices, maybe the budgets are really tight. For whatever reasons, this equipment just is not getting the kind of attention that it needs to get. I like this one. You got a piece of equipment, process cooling unit in a back room, and now you got a fan on it to try to keep it cool enough so you can keep it running. clogged up filters on the left. You've got leaks, the rust on the blocks, the leaks. These are obvious problems. If you've been around the manufacturing world and you walk through some plants, you will see equipment that just really needs some attention, and you just suspect that it's probably either not long for the world or not doing the job right. But how do you know? These motors may have a little bit of rust on them, but heck, those motors might be 3 or 4 years old. Maybe there's still a lot of useful life on them. So you can even get yourself misled sometimes by thinking that something needs to be replaced, but in reality, its environment just needs to be improved. And that's the genesis for a lot of CIL programs: clean, inspect, lubricate, to improve maintenance and performance. The idea being, if something starts to drip, fix it so that the drip doesn't get bigger. It's kind of a pain to fix leaks, but on the other hand, it's a lot cheaper than letting the leak get bigger and bigger and eventually causing a shutdown, which becomes very expensive. Old English phrase, an ounce of prevention is worth a pound of cure. But some problems aren't as obvious to owners. This is that chiller they were trying to keep online with a fan. And it's true that if a piece of equipment starts getting hot, it'll drop offline. But the other thing that'll drop it offline quickly is there's supposed to be about 100 tubes that you can see, and you can only see openings in a few of these tubes. They're clogged solid because of a poor water treatment program. 80%, maybe even 90% of these tubes are blocked. So how could an operating team not have caught a fouling problem like this sooner? You really aren't getting any cooling, and they're trouble keeping it online, and kind of going down the wrong path here on trying to get a fix for this particular chiller. Shouldn't they have known that? Why didn't they know that? And that's what we're going to talk about this afternoon. Try to get in the minds of the challenges that people have whenever they have to maintain equipment. And the truth is that when you're dealing with a lot of this mechanical and process equipment, the walkthrough, a CIL walkthrough, don't want to say it's not of value. It is. I believe in good housekeeping, and I believe in value, but just because you do it doesn't mean you're picking everything up. It could just be kind of a surface thing, kind of like these batting averages that we were looking at. If you don't dig in, you don't turn this into knowledge and understand what's going on, then you can end up with very expensive problems. Fouled heat exchangers and coils. You could have a pretty nice housekeeping going on your hand, and you could have clogged up chiller tubes because they're out of sight. They're inside the equipment and hidden from view. Pump impellers can totally get ground away with time. So your 10-inch impeller turns into a 9-inch impeller, and that pump only pumps 70% of the fluid it's supposed to. If you leave it go, it'll be 60%, 6 inches pretty soon, and only 60% of the fluid will flow. You could have clogged up filter coil sections that really reduce air and liquid flows. I see a lot of pressure and temperature gauges, and it's not uncommon. I said, boy, that looks like a high temperature, and the answer will come back, well, yeah, but we don't trust that. That's out of calibration. And sure enough, there's an electronic instrument they trust more. And there's a 4 or 5 degree difference between the two of them. So which one to believe? Very common problem. You have instruments, you just don't believe them. You can't believe them. You can have partially closed valves, valve seats that leak, and other things that you think you got something closed. It's not. Things that get blocked, strainers and filters, just on and on and on. And all of these are invisible on a walkthrough. You just can't see it. So here's a question. That's a pretty nice 3-pump set. Good installation, good foundation, it's clean. But how do you know that those pumps are actually in good repair? It's not obvious. We aren't showing a lot of pipe, but pressure gauges, how do you know? How do you know what's going on with these pumps? How do you know what's going on with these air compressors? You'd think they look good, but I've seen compressors like that, and one of those compressors just won't work. Can't even get it to run. So it just so how do you know? How do you know if you're operating well, if you're operating per design? How do you know if you're going to have a problem? Same with this heat exchanger. That chiller tube, that was just a heat exchanger. That's what this bundle is full of. It's full of 1/2-inch tubes on the inside. You're taking heat out of a hot stream and putting it into a cold stream. If you got bad water treatment or bad fluid treatment, you could be totally gunked up. There could be no cooling going on here at all, or heating, whatever it needs to do. So is it fouled? If so, when do you schedule it for cleaning? I like this. I always call these shark tooths. I see them referred to sometimes as sawtooth combs, sawtooth curves. But basically, when you're dealing with heat exchangers, you deal a lot with fouling factor, which is a measure of how dirty is a surface getting. And you start clean with clean tubes, and you get a certain amount of heat transfer. And then there's usually a cap. You want to go up to the dirty line. And when it gets to that point, it's time to shut down the process for a while, and you'll clean it. You could rot out the tubes, or a lot of times it's an acid wash or something that cleans the tubes. And what we're just showing here is you got to do it. It's just part of the ongoing operating thing, the process people get into all the time with their heat exchangers. How do you know when it's dirty? I've seen a lot of temperatures, but dirty requires a calculation. It requires a fouling factor, and I don't see that popping out of a lot of control systems. So you have the dealing with the mean time between cleaning, and how do you make that greater? If we spread it out, obviously it's more runtime, more operation for the process. Another real world example, sometimes it's really nice to fly, the first time you fly, you don't, you just do it visually, and you got to wait for clear days. And boy, it's a beautiful sight. But we'd have a lot of problems with air traffic if we didn't have pilots that could fly through clouds and fogs. And how do they do that? And they fly by instruments. They rely on those instruments to see what the human eye can't see, because we're limited with the human eye. And flying by instruments, I saw this picture and I couldn't redo. So don't be confused with this as instrument flying. That's a scene out of the old farce airplane. So let's start getting into, and this is where I realize that we got a lot to cover, and I just really am going to focus a lot on a pump. Nice simple bite here on level 1. So here, another pump installation. Is it working properly? And before you answer yes, here are some questions. Is the discharge pressure within the design range? Is it receiving proper suction pressure? I don't see any pressure gauges here. There I can see a couple of pieces here and there, but can you really answer all the questions? Is the pressure drop across the strainer too high? Are valves positioned properly? Are there limit switches on valves? Is the right amount of flow being circulated? There's not a flow meter here, maybe somewhere else in the system. And these are important questions to answer because when an engineer designs the pump, it's around this very specific point. We have the differential head. Another way of saying that would be the pressure difference across the suction and the outlet. And every pump's going to have a characteristic curve. And on the x-axis, you plot flow. And it makes sense. The more you flow, the lower the pressure. This is the capacity, the performance curve of the pump. And the point here marked with a little angle is the design point. So the engineer wanted that amount of flow at that pressure drop in order to assure that all of the equipment downstream was getting the proper amount of flow. And you can also see with these slanted horizontal lines here, these are the horsepower, the power lines. how much power is required to drive the pump. So as you go to the right, you need more and more power because power usage goes up with the square of the flow, but directly with the differential head. So the more flow you get, the more power you need. And you can see a problem here. You know, if you put in a wrong size motor, if you start dropping your pressure some, it's almost counterintuitive. If your differential pressure goes down on a pump, you actually use more horsepower. And when you do that, you could run out on a pump curve and you could overload your motor. A lot of things to think about if you're an operator. So let's look at some different operating points. We could, if we came in at A, you know, if we took the readings and said, hey, you are operating at point A, well, that's great. We'll give that a thumbs up. But I've also seen a lot of pumps operating at B. Well, that means the balance is a problem, or there's some bypassing going on in the system. So the system's not healthy when it's operating at B, even though it's on the pump curve. You could have the other problem. You go on C, you could have some equipment blockages because you got higher pressure, maybe your valve. You got some low flows in some of your equipment because you aren't flowing enough water, so you're going to have cooling problems throughout the system. What if you end up at point D? Well, that could be an impeller issue. It could be a suction issue. So pumps are real simple devices, but all kinds of things go wrong with them. And as you start looking at the pumps that are installed in industry, how many of them really are operating really at that point A where they need to be? Kind of like cars. See cars on the road all the time, but they break down. So how do you know which one's going to break down next? Some people get stranded more frequently than others. My dad was an equipment operator, and he would talk about being gentle on the equipment. And there were other equipment operators the mechanics did not want to see get into a piece of equipment because they weren't gentle with the equipment. They applied the brakes too quickly. They jerked on acceleration, you know, moving the equipment, and they experienced a lot more breakdowns. Cars do the same thing. So some people have bad luck with cars. Well, sometimes the bad luck is coming from personal error, just poor driving practices. So when we start getting into this maintenance, and sometimes it helps to get out of this field. We're so close to engineering and in industry that sometimes it just kind of helps to look at, well, how do other people do this? And let's think of medicine. Let's think of doctors. There's just mechanics for the human body. They're maintenance people. How do they go about this? And I hear pictures of some seniors, and interesting piece of data. If once you hit 65-year-old, you have a 2.5% per year chance of having a heart attack. So these are seniors, they're at risk of having a heart attack. That's a pretty good chance, and that's per year. So just because you escaped at 65, you still have another 2.5% at 66. So obviously the heart's a real big piece of us living into our old age in a healthy way and being active. So how do doctors deal with this kind of a rate of failure? Well, I think they go across the spectrum. Because sometimes things just break. You have the heart attack and it is a breakdown. And now it's emergency surgery, emergency stent insertions, and if you're successful and you get off the table, you are going to come up with a regimen of a lot of heavy-duty medications, exercises, checkups, restrictive diets to try to make sure it doesn't happen again. But you don't want to be doing breakdown maintenance. That's really what they try to get away from. And we see it on TV and the news and everything else. How are we trying to get away from it? Because breakdown maintenance is really, really expensive. It's overtime. You're pulling people in at 3 a.m. and you have to drive distance. You have to fly equipment in. It's very, very expensive. So the buzzword in the 70s and the 80s was, well, what about preventive maintenance? You know, you do some checks, you understand a person's starting to get some aches and pains, and maybe it's time, and they're up in that age group. So let's look at scheduling surgery. chances are a lot better then. It's not emergency, everybody's fresh, you've gotten properly prepared. A lot less risk involved with preventive type of medicine than there is breakdown medicine. But you're still undergoing a pretty significant procedure, right? You've got to do stents, you've got to, and you've still got the heavy medications, the exercises, then diets. It's you're on the verge of breaking down. Better than breaking down, but you're still on the verge of it. Not a good place to be. So where medicine likes to be is into these next two categories. We can do condition-based. Let's check blood for proper condition, because we know that the heart usually doesn't just quit. It usually starts giving you signals. You have the chemistry issue in your bloodstream. And now by taking proper medications, statins and other things, and proper diet and exercise, they're going to correct the problem so we never have to deal with these kind of preventive procedures. But where we'd really like to be is on the predictive side. You're 30, 40, 50 years old, you're getting up into that time, you're getting into a higher risk category. Be active, have an active life, eat the right foods, exercise properly. And if you do that, occasionally see a doctor and confirm that everything's on track and you don't have some rare genetic anomaly that's going to put you into a higher risk category, you can live a longer, healthier life and reduce your chances of failure. Perfect analogy to how we need to go about thinking about maintaining and operating our plants. And it's at too many sites, and this is particularly true as we've gotten tighter and tighter on staffing. So many sites are dealing in the breakdown preventive mode, and there's just no reason for it anymore. We can do better. But it's a good test. It's a good question. Where is your plant? What's your percent of unplanned outages? Where are you at? And what can you do to make this better? So one basic test I like to do, I don't maintain my own car. I've got a good mechanic that does that, but I do check gas mileage. So here you've got a car. It's designed to go 40 miles per gallon. You check it after a couple of months, and you find out you're only getting 39 miles per gallon, which is 16.5 kilometers per liter. A couple more months, you're down to 35 miles per gallon. That car is telling you something's not right. I don't know what it is. It could be an air filter issue. It could be the fuel quality you're using. It could be the way you're driving. It could be a lot of things, but it's starting to talk to you because you aren't hitting design condition anymore. And I'll tell you that it's a lot easier to go from case 1 to design than it is case 2 to design. So if you just keep letting things go, eventually you get down the path that you start getting into the failure mode. So good maintenance of automobiles, of equipment in general, means paying attention to it, listening to it, finding out when it's in stress and addressing it early. That's the ounce of prevention equals a pound of cure. Great looking chiller here. It's a large chiller and great looking, but how do we know that it's not showing some signs of stress? Can't tell by looking at it, because obviously they're paying a lot of attention here to housekeeping, but that doesn't tell you how these pumps are working on the compressors and whether those heat exchange surfaces are clean. And there are a lot of stress indicators that a good control system can pull out for you. It can look at efficiencies. What's a kilowatts per ton? What's a kilowatts per kilowatt of refrigeration? Are you at design? Are you not at design? What kind of pressures are you dealing with? Are the pressures starting to increase? Are they decreasing? Are they at design? Temperatures the same way? Flows, are you getting the right amount of flow on the cooling tower side, the chiller side? Is it starting to make some noises? Are the vibrations starting to increase? How about an oil analysis? Is that a problem? Start putting yourself in the mind of an average technician or operator out there, and that chiller is just a single piece of equipment, but it can't run without, in this case, 3 pumps running. It's got a cooling tower, and every one of these pieces of equipment can go bad. and will go bad with time. You know, cooling tower water could be too warm. Well, you aren't going to get chilled water if the cooling tower is too warm. Your pump, is it okay? Not okay? Fouled surfaces because of poor water treatment systems. Get too little flow going around the loops. You aren't getting the heat back from the heat source, you know, et cetera, et cetera, et cetera. And this technician has got to figure all that out. And what's the likelihood in a simple system like this that everything is working 100% per design? Say probably not too good. Chances are pretty good. Some pump is flowing too much water. Some pump is flowing too little water. There's a control valve hitch. Something's out of calibration. There are a lot of pieces here, even in a simple system like this. And this is probably more typical of a system in a typical plant, you know, where you've got a couple of boilers, you got a couple of chillers, you got several pumps. Could be quite a mess. It's quite a challenge to keep a system like this up and running. And how do you do it unless you can see and hear what's going on in these pipes and the heat exchange surfaces and the others? So without that robust data acquisition and control system, you could sit there and stare at this system and you can't really tell because you're dealing with some small differences sometimes. You know, I want chiller temperatures at 10 degrees Celsius. It's 12 degrees Celsius. I can't put my hand on a pipe and figure that out. That's too close, but that's a 20% difference in the amount of cooling that I might be getting on my process. So that could be the difference between having the right humidity and making good product or not. This is a screen. I grabbed this. It's not one of ours, but I grabbed this. I thought it was a pretty typical screen of what I see. And most people would look at this and they'd say, you know, yeah, it's a good control system. And to folks' credit, they've put money in electronic controls. They've put good money on in TV screens and monitors. And it's giving a lot of data. But I would argue it's not giving much knowledge, because it took me a while to read this. It wasn't popping out. I was trying to understand these numbers and what I could glean from this. And so, well, those two chillers aren't even running on this day. So equipment A is not operating. They got a balancing problem going on here. They shouldn't be mixing warm water and cold water with this remaining chiller that's running. So that's a problem that's going to cost them energy. I was just kind of noting that obviously this is a tall building they're in, and this is a basement floor type of installation. Pick that up from the pressures. You have variable speed pumps, and they're working harder than they need. They spent money on variable speed pumps, but there should be a 10-degree delta T in the system, and they're running at 1.1 degree delta T. They're pumping 3 or 4 times as much liquid as they should on a design, you know, per design. And because of the cool outside temperatures, I'm not seeing free cooling heat exchanger in here, but they would have the opportunity to do better on the sustainability, particularly in the winter and summer months. So just that little bit of data, you know, you start converting it to some knowledge, and what's it telling you? You say, well, that system needs some attention. So I want to give you a sample problem, and we're going to go through it pretty quickly, but this is a real problem from our files. You know, it's going back 15 years or so. I had a client call and said, I got a problem, Mike. I got this process heat exchanger, and I can't get enough cooling. I'm supposed to be making 200 pounds per hour of product, and I'm only making 100 pounds per hour of product. You know, it's half the design rate. And the problem with that, it's costing me $200,000 per year, because I should be able to, at design rates, get everything done in one shift. It's forced me into a second shift, and I can't figure it out. So we went out and looked at it, and this is kind of what I saw. So, you know, we saw the pump curves, right? You know, what does a pump need to do? Well, you need pressure in and pressure out. There was no pressure gauge. I couldn't tell whether the pump was working or not. And the other important thing to talk about here is they were coming off of a a reservoir. So that's a pressurized supply pump. So this is a booster pump. This isn't coming directly from the water source. It's a booster pump. So we started looking at it, pulled the pump curve and say, yep, this is where we wanted to design, so we thought because the temperatures on the heat exchanger looked okay, we were probably okay there, but we didn't, so we were really focusing on the pump. But here I've got the pump, I got no gauges, I'm flying blind, I'm looking at it. It's not making noise, it's running smoothly, the motor's spinning, and it always spins, and they've never had an issue. So we decided to, I had them work on a weekend when they were down and throw in just a couple of pressure gauges and took an amp reading on the motor. And boy, when we did that, look at what happened. We found the entering pressure was 40 pounds, leaving pressure was 40 pounds. And so we had no differential pressure. We were at 0. And the amperage was only 30% of the rating. So we were operating way down in this low flow range. So then we had them pull the pump apart, and absolutely no impeller. This pump had been working for 5 years every day. It was a real soldier, spinning, and all we had was the shaft of the pump left. The impeller had eroded long ago, and it was costing them $200,000 a year. It was $1 million problem. The repair cost for a new impeller, $2,300, and then they're back in business and making product the way they were supposed to. So it really a little bit of knowledge to pump controls, and so the question is, well, what does that knowledge look like? And I've got a little screen here that we'll go through again kind of quickly, but I think you're starting to get the idea of what we want to look at. We want the controls, since we've already invested money in controls. Most pumps have a pressure transmitter on them. I don't see a lot of installations going in without pressure transmitters. I don't see a lot going in without some kind of building automation system. So we've got a lot of the hardware we need. We might be missing a couple of pieces. We are missing a couple of pieces, but we're about 80% of the way there. If we could just do that a little bit better and be a lot smarter about what do we do with the data to try to package it up so the technician could see it better, then we've got a real opportunity to help people do a better job of keeping these systems reliable and cost effective. So the input data we need to know where this system is operating on its curve. And it's easy for us to put together an equation to curve fit a performance drive. And what's shown in green here on the is what's acceptable. The acceptable range. Obviously, you can't be 100% dead on the spot, but if you're within 2%, 5%, pick a range. There's an allowed variance that you can have on this pump. That's all we want to do. We want to know what the design point is, and we want to make sure that we're in that allowable range on things like flow and pressure drop. And we need to check amperage so we can know if we start getting some calibration issues with instruments. And then with the input data, we can start calculating some values. What's the actual differential head? What's the actual brake horsepower? What's the actual efficiency, et cetera, et cetera. So by using the knowledge, we can compare outputs versus design and then alert. The key is if you're a little bit out, this is like my car not getting as good a fuel mileage as it should. If I'm a little bit out, I would want to alert the technician team that something's not right here. It's starting to go bad, so it can be put on a maintenance schedule, an operating schedule, and we're trying to alert people, give them time to respond, get it back at design before there's an alarm, because alarms are usually bad. Alarms mean I don't have enough pressure to keep the process running. I don't have enough I don't have the right temperature in order to make quality products. So we're trying to build a second piece in, a flag, an alert to the operating team and maintenance team. So here are some potential troubleshooting alerts that we can do with a pump, and we've done this at a project that we did a few years back out at the Cincinnati airport. We can look at total differential head. What's the actual, and is it less than the design minus that allowable total differential head variance? Well, if it is, we know then we can start informing people, informing the technician, maybe you got an impeller issue it's going bad, or maybe there's a balancing valve issue, or maybe they got some instrument calibration problems. You can flip it around the other way. What if the TDH is too high? Well, it could be a valve or equipment blockage. It could be an instrument calibration issue. Again, it's pretty easy then to start programming troubleshooting tips into the system once we have just a little bit of knowledge. Do the same thing with amperage, cross-checking flow meters, TDH, and it's an important measurement to make sure that our instruments are calibrated, and we can start flagging a calibration issue. Suction pressure is too low. You kind of get the point that every one of these potential alerts, again, a pump is a pretty simple piece of equipment, but you can start seeing where the complexity is. And if you don't provide the controls or at least the data for all these things, how do we expect a technician to troubleshoot properly? You could even step it up a notch. You know, you could add vibration on real major equipment, and pull those out. It's probably fair to ask, well, why don't our systems operate as they were designed, constructed, and commissioned? And the answer is, I think they're actually pretty robust, but nothing lasts forever. Go back to the car. I don't remember the last time I kept my car over 100,000 miles. Even if you buy a new one, you get rid of it, you get tired of it, you buy one that's a year or two old. 100,000 miles, 160,000 kilometers, that's a pretty good life for my cars as far as keeping them. And I started thinking, well, how many oil changes do I have in that time? How many new tires? How many minor repairs, breakdowns, etc.? So if I drive an average of 40 miles per hour, 60 some kilometers per hour, that 100,000 miles translates to 2,500 hours of operating time for that car. Compared to what we're asking for a pump, we have 8,760 hours in a year. These pumps are doing 6,000 hours, even if they're running 5 days a week. More than 8,000 hours if they're running 7 days a week. So, a typical piece of equipment in our plants runs 3 times as much in each year than my car does in its lifetime with me. This is good equipment. That's why it's so expensive compared to a regular automobile. So, wanted to summarize some operational reliability checks. We need to make sure that we have instruments calibrated. Variable speed drives, which that one screen that I showed had, are they operating at the proper speed? I don't remember the last time I've seen any cross check, from a control system say. I see a lot that say, yep, it's operating at 85% speed. But then I see a lot of those that also have differential temperatures that are too low, so I know there's a balancing problem so there's nothing that really flags, hey, it shouldn't have to operate at this speed. It is, but it shouldn't have to. Why is that an issue? Energy costs are higher year-round, but the big thing is you start getting the heat of the summer, are you really going to have enough cooling where you need it? The pumps operating on the curves, we've talked that, bypass valves leaking, dampers leaking, pump vibrations within limits. So, being smart costs some money. I think probably some brain power, really thinking through things as much as that. So that translates to money, some resources. But ignorance costs a lot more. Think about this pump with no impeller, it's $1 million a year. Simple example that cost a lot, but there are a lot of examples out there that are costing people money. What do we need in the way of hardware? Some field instrumentation, pressures, flow meter, really important to know flows. Electronically, a watt meter or at least an amp meter, and then that gives us some cross checks to check the calibration. I know one of the stumbling blocks is on flows. Flow meters can get expensive, but there are some workarounds. There are some devices you can put in the lines that are more manual, and they give you an opportunity, kind of like an orifice plate, to take some readings maybe once a month or so to kind of cross check and make sure the flows are right. You could assume that the flow is going to be right in between readings, so that's a way to save some money. Another way, some of our equipment like chillers are really good for this. They'll look at the pressure drop. They have some internal pressures, and they back calculate flows based on their pressures. So I'm not an advocate of putting in extra instrumentation. If we can be creative and make use of packaged equipment and its data, then by all means we should be doing that. And what are the benefits? Well, the reason we put systems in the first place is we've got to meet some core business need. We got to make a product, a certain quantity of product, a certain quality of product. And if we've got a combination of equipment and systems that aren't doing a good job of that, then why even spend the money on it and do it? And that usually comes down to, are we getting the right flows, temperatures, pressures, heat transfers out of the equipment? And because a lot of commissioning was done when these systems were put in new. Are they continuing to run that way day in and day out? And we know it's certain that things will decay with time unless there's a timely and proper intervention on the maintenance and the operating side. These systems need to be there all the time. They need to operate reliably. We can't be having a lot of outages. It's very expensive to have outages, people standing around and not actually producing a product when it was designed to. So the more we can get rid of unplanned outages and costly breakdown maintenance, the more money we save. And of course, everybody's interested in sustainability as well. On the software side, a lot of folks, a lot of times this is already installed. So, maybe there's an extra board, maybe it's another model that needs to be upgraded. But there are a lot of SCADA systems in operation, and they have some capability to do a better job of trying to turn data into knowledge. And we can certainly get alerts and alarms and second, and in fact people already do a lot of that. Okay, primary alarms, secondary alarms, that's really what we're dealing with. So a lot of those features are built in as part of core functions, but the programming just needs to be thought through. And in the grand world of controls, most of this process equipment really doesn't tax these systems that much. Think of like a packing line. You got to go through, a control system needs to go through in milliseconds, constantly adjusting. Well, process systems and utility systems are really, in the computer world, very slow sampling rates. 5 seconds in my book would be a fast rate. You don't need that feedback that quickly, so you don't need to be spending a lot of money on the latest type of processor. And the big problem with a lot of data, you just keep getting more and more data, and now you have to worry about memory, although less of a problem with memory now since the prices have come down so much over the years. But where do you store the data? Where do you locate it? How do you keep it secure? The value of the historical trending. How do you back it up? Because you don't want to lose it if you want to go back and try to troubleshoot problems in the past. Again, a lot of people are doing a lot of good things around answering and addressing those questions. I think it's one of those issues where it's not that money's not being spent here. A lot of money's being spent. The whole message here is we can think through this and do an even better job of turning that data into knowledge. Let's put this equipment to controlled equipment and SCADA systems to better use. Here's some basic tips on the human-machine interface. Password protection. Again, a lot of folks know a lot about this, a lot more than I know about this. So we can start where it starts coming into my play as a systems engineer is on the alerts and the alarms. I don't think you'd want to or need to redo anything with these systems that you aren't already doing as far as design practices go. And I think the last one, transparency, is a really important point. We want to make sure that this smart data, what I'm calling smart data, where we've turned some data into knowledge that's really helpful for the technician and the operating team, we want to make sure that it's readily available and it is as easy to use as the direct operating data. And maybe it's even, we want it easier to use because it is the prime conclusion. If you're reading a newspaper article, it would be the headline. It would be the top paragraph. If you want to get into more details, by all means, we need to make sure that that data is available. But 90% of what we can get out of our newspaper articles is that front page, just reading the top lines and the first couple of paragraphs, and we can start getting into a pretty good understanding of what's going on. And I think that's where, when we do that, it really helps the operating teams with their jobs. So how do you hold down costs? Set a priority list. Obviously, some systems are more important than others. They're critical to process. It's a critical process packing line. It's a critical process making system. So you'd want to focus on those high priority systems first, but that doesn't mean that all systems won't actually benefit. I like the idea of using existing instruments and measurements as much as possible. If package controls, if you have a process heater that's already measuring temperatures in and out, why spend money on another temperature transmitter? Or why spend money on, for heaven's sakes, a manual gauge that can't get the data back into the control system so you can manipulate it? So I really like the idea of upgrading and do one thing right. Don't take the same temperature 3 different times by 3 different pieces of equipment. Just do it once, and then we can look at calibration. If that temperature transmitter is bad, then we know, and we can flag it and then get on top of it. And then finally, if it's really unaffordable, a flow meter is just really difficult, and they can be. It's not just the cost of the flow meter, but you have to have lengths of straight pipe before and after. Maybe you have to get clever sometimes, perform some calculations based on a couple of flow meters that are easier to install, and you add them together. I think all that's okay, because when you think about it, it's a lot better than what's going on now. And for a technician to try to figure out what's going on now, that's exactly what they would need to do in the field. So in summary, system owners are empowered, with knowledge, help to reduce maintenance, energy, operating costs, and it really is possible to get more out of existing investment that you have in these control systems. Getting close to the end of our time, and wanted to point out that if you need a professional development hour, send us an email, and we will send you a certificate for today's class. And really appreciate your attendance, and are happy to provide that. If you have any questions, there's a chat screen, or you can email them to us, and we'll do our best to get back with you as quickly as we can. We've scheduled the next webinar for Tuesday, May 14th. Discussion topic, we're going to continue with the smart controls. We're going to take it to level 2, and we'll probably talk about some of the other equipment. We've talked about pumps, but what about fans, heat exchangers, and some of the other equipment and other thoughts that start coming into play in our typical manufacturing plants. And then finally, I'd like to thank you for participating and attending, and we really appreciate all of the input that we get when we do these as well. I will leave this slide up for the next 15 minutes or so you can take down information. But again, don't hesitate to contact by phone or email, and we're happy to respond and get back with you as quickly as we can. So thank you very much. Appreciate your attentiveness, and have a great day.